welcome all. Welcome to our session on learning from DMDU and complexity. I'm actually really excited about this session. Many years ago, when I first got involved in the work that became decision making under deep uncertainty, we actually focused on complexity and models using complexity. And for many years then switched to more deterministic models. But complexity in many ways sort of seems at the heart of some of the ideas at DMDU. And I love the sort of the notion that complex systems are ones that can be understood but not necessarily predicted, which makes them sort of the sort of quintessential object of study for DMDU. And so I think we've got a great lineup today, a mix of people who have been involved with the DMDU Society since the beginning, and some people who do great work in complexity but are new connecting to the society. And with that, let me turn over to Edmundo and what should be a really great session.
Thank you very much, Rob. We're going to start with a presentation from Tim McDonald. He's assistant policy researcher at the RAND Corporation and also a PhD student at the Pardee RAND Graduate School, and also a senior fellow at the Center for Policy Design, and previously has worked also as a researcher at the Harvard Kennedy School. So without further ado, Tim, the floor is yours. Whenever you want to start, please go ahead.
Sounds good. Yeah, so this presentation is about, it's essentially about leadership and about trying to transform large complex systems. And it's, focusing on a case study on Mexican health reform, in part because this case that I'll talk about briefly is kind of a quintessential example of trying to change a complex system, but it also in honor of our hosts based in Mexico. The presentation structure here, I'll lay out the policy challenge as I see it, and then tell a very quick story, very, very quick overview of the reforms in Mexico, and talk a bit about what we can learn from it as a model of system change. And the intention is to take some steps toward developing a theory of system transition. So I'll state a few postulates here. One is that achieving our aspirations as a society, achieving our goals, requires well-designed systems. They could be our health systems, education, and economy, many systems. The systems are complex and they exist in a context of deep uncertainty. And also the systems need to be updated regularly and sometimes fundamentally redesigned to align with our aspirations. So, we may have an education system, for example, that is successful at providing education to an entire country, but it may not be set up to perform at a high level. And that's a different set of goals, and there's a fundamental design problem of the system. So sometimes these systems need to be redesigned. But the question is, if and when that happens, when you need to redesign a system, how do you lead deliberate efforts to do that, particularly given that these are highly complex systems? And very quickly here, I want to run through a lens of complexity applied to systems like this. Complexity has implications for how we think of how the systems are structured. There are a hierarchy of nested systems. So for example, a family unit exists in a home, which exists in a society, but you're also part of an economy. There are many interdependent components, different elements within the system. If they're animate, they have their own interests and their own calculations, their own functions. The complexity has implications for the character of the systems. They're uncertain. There is a temporal dimension. Systems have different characters over time, and there are emergent properties, and also how the systems change. So specifically complex adaptive systems, they're continually evolving as the agents within the system are adapting to changes amongst other elements in the system, to changes in the structure of the system. So I kind of lay this out because the implications then for how systems change. there almost never, even in a country like China, there almost never is a authoritarian figure that can wave a wand and you magically change a system. And that's just a fundamental framing issue for how we think about the change of systems. There are many parties, they have their own interests, there are many levers of power, there are many sources of authority. And so when you want to change a system, you'll need to institute usually many changes over time. And so very kind of 30,000 foot here, I'll talk about reforms that occurred in Mexico. 2002, half the population doesn't have insurance. So there's a few different systems there. If you're part of a formal employer, you get health insurance through the formal employer. If you work for the government, you get insurance through the government. If you're in the informal economy, which is half the country, you did not have health coverage. 2003, the government enacts Seguro Popular, which is a popular health insurance program. It covers the uninsured. Over time, it allocates an additional 1% of GDP to the health system. And by 2012, Mexico achieves universal coverage. This was 53 million people that did not have coverage, that got health coverage. So I'll run through a timeline here of what happened. This is about 20 years. There's a lot of significant buildup to this, and there's been a whole lot that's been going on since this timeline ends. But essentially, some of the key milestones here, there's a Mexican Health Foundation is formed in the 90s. It performs really essential public health research and health system research, building the understanding of the state of health in Mexico. Around 2000, the World Health Organization publishes a model where they assess the health of different national health systems, and Mexico fares very poorly. And this was kind of a shock to the country. They thought, at least relative to their peer countries, they had a good health system, but it turns out when you look at public health metrics, when you look at financial exposure people experience, Mexico was not situated well. In 2000, Vicente Fox is elected president. He's from the PAN party. It's the first time that a second party is elected to the executive office. And so there's not a deep bench of people that have, this is the first time the party's been in power. There's not a deep bench of people with experience at the ministerial level. So he's looking around for talented people and people with ideas. And he finds a guy who's a Mexican physician who's at the World Health Organization, had been involved in building the model I described, Julio Frank, and he appoints him health minister. And, you know, Fox is also looking for ideas. And Julio Frank has, for a long time, he's been involved in building up the evidence base for the need to have greater health coverage in Mexico. And so they design a series of reforms which fall under the Seguro Popular. They get them enacted. There's sort of a whole series of events, but they enact them at the legislative level. They begin implementing them initially with pilots at the state level. There's a lot of mechanics that are going in here, going into this. There's a key financing mechanism that allocates a certain portion of economic growth to the health system that changes the flow of the money, and that ends up being a key mechanism. But they pilot the program with 6 states, and then they go national. It's essentially money going into health coverage, and then also building up the physical infrastructure of the health system and developing people as physicians and nurses. Felipe Calderon's elected. He has many things on his plate, many pressing priorities. Crime and drugs are a significant one, but he chooses to continue the implementation. External review and evaluation of the program begins. In about 2007, Gary King at Harvard leads a major evaluation. And really the Mexican Health Foundation, there's a little arrow running through here, is doing research and analysis the whole time, and it's being fed into the policymaking process. Various ongoing challenges were building up the system capacity, dealing with governance and controls. Money's going out to the states, and some states are handling it well, some are not, but there's sort of ongoing issues. But by 2012, they achieved the universal coverage. So that is, you know, sort of a woefully inadequate but essential overview. So what can we learn about how systems transform if we use this as an example? I put just a statement here, a principle for system transformation. We can change a complex system by affecting its evolution through changes to either the structure, the elements and the relationships, or system attributes, the values, functions, priorities within the system. So, in the Mexican case, one of the big things was the flow of money and creating a new financing mechanism and reallocating part of economic growth to health. But there was also the creation of new training infrastructure for medical personnel and the creation of new institutions. And those new institutions essentially became new elements within the system. And then a lot of the leadership at the national level and the publishing of the studies that showed that Mexico was comparatively poor compared to performance metrics compared to their peers, which surprised people, helped change the culture and the tone around health. There are a couple of related concepts here from the IPCC. System transformation, a change in the fundamental attributes of a system, and then system transition, the process of changing from one state or condition to another. So the question is, if you want to change from one state to another, how you do that. And I posit there are two basic approaches. One would be changing the system design. The other would be through stewardship of the system. And I'll focus here on the system design. Outlining here two basic steps to changing system design. The first is developing a future model. The second, adaptive implementation. And this is essentially what the Mexico group followed. So first, developing a future model. I outline here a series of steps that were taken. Determine the goals for a system, map a system, identify problems in the system, which are defined formally as the discrepancy between goals and actual performance of the system. Diagnose the causes of the problems, which usually has to do with incentives, and then develop a new proposed system design. And the future model that you have in hand then is your mountain in the distance. And the idea is not that you're implementing this perfectly, but this is where you're heading. This is the direction you're heading. And so how do you implement a future model? And there's a metaphor of a log jam that I find very helpful. Log jams occur, you cut down some forests in Canada and you send the logs down a river, and the logs end up coming to a pass and they get bunched up and basically form a giant dam. How do you clear a complex, interdependent jam where you can't bust it open all at once? 3 steps. First, you always be looking for and working on the front log, which is the step or action most likely to imbalance the status quo and move the jam toward your desired future model. Working on the front log means finding and persuading those with the interest or power and motivation to take the action. So in Mexico, the first step was getting the research through the Mexican Health Foundation, then the World Health Organization publishing its report, and then getting the public officials and labor involved in development of Seguro Popular. It's sort of a sequence of events. This becomes a fluid, iterative situation. So you're always looking for the front log. You're always finding people who can help you move it. The question then becomes how you organize this type of activity. And one model, I'll put some principles here first. It needs to be independent and informal because it needs to occur over a long period of time. Progress is measured in decades. You convene and involve stakeholders, clarify the central questions always. You're chasing a vision, a very clear vision, and you're always developing proposals for action, and then you're always working on the front log in the jam. And there's a model that a project Rob led that I worked on. We called it a shadow process, working with the city, and defined it as a structured exercise that runs alongside formal planning processes that government might use. But it's independent, and it might involve stakeholders from the government, but they leave their hat at the door and they're exploring, experimenting with different ideas and feeding them back into formal processes. But if it's independent, it allows you to deal with the ebbs and flows of politics and people going in and out of power. And it allows different stakeholder groups to come together, many of which may not agree all the time. And so, this is a work in progress, and what I'm doing is expanding into other case studies with the intention of building a framework that has some general applicability. So anyone that's trying to deal with system change can apply these principles. And so, any comments, very interested, we can talk here offline. Thank you.
Thank you very much, Tim. All right, so now it's my turn. Let me bring my slides up. Perfect. There we go. All right, so I will discuss this presentation is titled Computational Intelligence for Sustainability Challenges. I'm Edmundo Molina, a professor at the associate professor at the School of Government of Tecnológico de Monterrey. There you can see my Twitter handle and my website if you want to get in touch after the presentation. Why we need computational intelligence to study sustainability challenges for IDS mainly. Well, we know that human and environmental spheres are complex systems because they have a lot of interdependencies and path dependency and emerging behavior. We also know that deep uncertainty affects both the spheres, just as Rob was mentioning. Maybe this is actually an inherent characteristic of complex systems, is their unpredictable or volatile behavior. The challenge for policy analysis is that if you oversimplify, then maybe you miss some critical information. If you make it extremely complex, maybe then irrelevant for supporting decision, actual real decisions. Modern computational tools, the premise here is that modern computational tools offer opportunities for circumventing these limitations, such as optimization using evolutionary algorithms, machine learning, and also visualization techniques, and other sort of computational intelligence tools. But what I will try to show you here is that really this is best harnessed when we use these tools in combination and integrated way. All right, so technological change is complex due to interdependencies across various systems. Here, what I'm displaying is 4 technologies, how they have diffused internationally, over the span of several decades, in some cases, more than 100 years. This is data from the CHAT data set. Work of Hoving and Diego Coming, a great, very unique data set. And what you can see here is that basically, technological change varies across technological platforms. So it's not something that you can really try to understand, understanding one way one technology diffuse globally is not going to help you understand how other technologies can diffuse globally. The second thing that I want you to pay attention to this, graphics is that it takes really a long time to make these global transitions. And that really speaks a lot of the challenges that we face with climate change. And finally, you can see that once you have a leader, it's not that the other countries can actually, quickly catch up with the leader. It actually takes a lot of time to be able to do so. The bottom point is that regions are inexorably connected. And for example, if the US decides to, leave the Paris Agreement, that is going to have, cascading effects internationally and over the long term. And if Japan or China or any other country sets very ambitious goals for carbon neutrality, that also is going to have an impact in the long term. So this all makes, technological change and climate policy complicated. My argument is that these are deeply uncertain phenomena. Technological change, on the one hand, is we never know how quickly and what is the scope of technological progress. And we have no idea of how long it may take to actually diffuse these complex technologies. And climate change, as you know, there's a lot of uncertainties, especially with how much temperature can rise and what is the speed of this change. This complicates debate because basically these uncertainties are intertwined. So we need to know what sort of technologies will be the future to define a climate policy response that we cap greenhouse gas emissions. At the same time, we need to know what is that appropriate level so we can control temperature rise. And if we think of what should be the optimal policy response, then all this becomes sort of like an uncertainty loop, because you need those parameters to actually understand what is the most cost-effective way of doing these changes. So over the last few years, I've been developing an integrated assessment model. It's a model that tries to address these issues by looking at the interconnection of technological change dynamics globally and climate change dynamics. and is based on how economic agents make decisions. What this model tries to capture is really some of the complexities and uncertainties of this policy context. To the left here, you're seeing sort of like more formally the mathematical structure of the model. The model is based on endogenous growth theory, which is actually, I mean, it's a very compelling and in a way, a quotation, a beautiful theory. Basically, the idea is that if you invest in technology, basically by developing human and developing new technologies, that change incentives of economic agents, that changes into temporal equilibrium conditions across economies, that of course, is going to affect the environment. And then, from a dynamic general equilibrium modeling perspective, then you can really study what is the best response across time if you want to balance, basically the effect of policy considering the utility of different agents. This is a beautiful theory, and as you know, sometimes we just fall in love with theories for the sake of how parsimonious and balanced they look like. I have been working on calibrating this model to actually real data using 50 years of GDP and fossil and renewable usage data, and what you are seeing here is a calibration attempt using bootstrapping for specifying a DAM to two regions, OECD and non-OECD countries. And this calibration actually has been very enlightening in terms of the type of challenges that one faces when actually trying to make a theory, test a theory in terms of its validity. What the model can be used for, well, all the effort for calibration of this model has been basically towards being able to monetize some of the policy descriptions. For example, what you can see here is one of the big things of the model is really trying to understand what should be sort of like the carbon price across regions and globally. But more importantly, what the model allows is that it's not only carbon price, what you need to actually accelerate technological change across these regions. You also need to understand how much you need to invest in developing in developing new technologies across regions, and how much you need to invest in incentivizing the usage, their usage, and all of that costs money. And it's just very important for us to understand, I mean, how much our budgets right now actually could be able to decarbonize the global economy in the long term. Let me just very briefly discuss an application of this modeling framework to, using an RDM approach. This is a table that describes an experiment we did looking at, various policies, and then how these policies in the context of this optimization exercise will behave across, a large set of scenarios, including various climate scenarios, various technological scenarios, in this case, captured by the assistive substitution, and various discount rate scenarios. And I'll discuss in a little bit more why we explore over the discount rate. So just a message here that EDIAM is, in addition, is calibrated to represent in an aggregated way various IPCC CIMMYT-5 general circulation models. This is a little bit an example of the experimental results. And what you can see here is on the horizontal axis is basically the penetration of renewable energy in the non-OECD countries, and penetration of renewable energy in OECD countries. And really what you can see is across this, and then color the nodes, basically what is the end of century temperature rise. And each panel is a different general circulation model. So what you can see, of course, there's a lot of variation in terms of, what could end up being the, end of century temperature rise given optimal policy response. And also you can see a very interesting interplay in terms of, in various simulations, actually, the non-OECD countries end up, diffusing more successfully technologies than in the OECD countries. But more generally, this happens more frequently in the OECD countries. When you have a model like this, and then you run it across a large ensemble of experiments of parameterizations, then you get an optimal vector. And then really the challenge becomes really, how do you understand what's happening with the optimal vector? So what does, this problem in terms of, formalizing cost and benefits tells you in terms of how the policy response should be adjusted if you face a higher or lower climate sensitivity, higher or lower elasticity substitution. And really what you can see in this heat map is just depending on what future you are facing, then and what policy constraints you have, then you either do more or less of the different components of policy. For example, if there's cooperation across regions, which is the panel B, then given that cooperation, then you're able to do more investment in technology and develop in technology uptake in the emerging economies versus not having that cooperation. And of course, we can use these sort of models in a vulnerability analysis context. And that, helps us understand basically what are the vulnerabilities that, basically, if you consider as an objective, keeping temperature rise below 1.5 degrees Celsius by the end of the century, then, using RDM, scenario discovery and vulnerability guidelines, we can really understand what are the drivers of that, vulnerability. And here's one of the things I want to point out. So in the experiment, we include the discount rate in the analysis, right? And as you know, the discount rate is a huge point of debate when it comes to climate policy. For example, if you look at the debate of Nordahl and Stern, there's a huge debate in the economic literature in terms of what is the appropriate discount rate for designing climate policy. When we do an experiment that expands over a large set of uncertainties, then you realize that maybe the discount rate is not as important as other drivers, such as climate sensitivity to greenhouse gas emissions and the elasticity of substitution of fossil and non-fossil technologies. So some lessons from the analysis. The combined application of multiple computational intelligence tools produces new insights. It helps us understand in more detailed way the effectiveness of different climate policy regimes. Integrated assessment models allows for the joint consideration of multiple regions and interaction between the economy. And as I mentioned, the discount rate is actually a very nice finding. Reflecting upon this work, maybe there's some hierarchy of how we can integrate models. And here the argument is that you need both optimization and integrated assessment models to kind of be able to explore what are the policy options. And then once you put that into an exploratory modeling exercise, through data visualization and machine learning, you can actually understand what is that optimal response telling you, what are the patterns that are shared across futures, what are the key elements of this response. We wrote a paper last year on this. If you want to learn more about it, here I leave you the reference. And with that, I conclude my presentation. And now we're going to turn to you, Konstantinos. So Dr. Konstantinos Kastikopoulos is head of research at the Department of Decision Analytics and Risk at the University of Southampton. And we're very pleased to have you here, Konstantinos.
Yes, hello everyone. I hope you can hear me and see my screen. So I will start immediately. I was very happy when I received the invitation from Tim and Rob. I didn't even know this society existed, so I'm very glad to find out that it does. And I'm going to show you an approach that with my colleagues have been working on for really decades, I would say, and culminated in a 3-year effort to write a book, which we did. And I'm going to try to outline it then. And this is how we view complexity, and that our answer to, I don't want to use a very big word, perhaps let's say our answer to sometimes understanding and sometimes predicting complexity is simplicity. So I will explain that first. Let me advance to my colleagues very quickly. Ozgur Simsek is the leader of the machine learning group at the University of Bath. Marcus Bookman is a senior data scientist at the Bank of England. And Gerd Gigerenzer is a leading cognitive scientist at the Max Planck for Human Development. So our code for complexity or deep uncertainty, they're not all the same, but we only have 12 minutes. So it's in the wild, hence the title of the book. So I'll introduce it. I'll try to explain what the wild is with a very English problem. Will it rain tomorrow? So this is Bertrand Russell. You can read what he said. So for us, this demonstrates well the problems with trying to reduce all kind of uncertainty into probability. We believe that in general, for the most interesting cases in health, wealth, justice, of course, it looks like in your society, you're grappling with systemic issues, which we probably don't, but let's consider individuals or small groups and their health, wealth, and whether they're treated fairly and treat others fairly in the world. I think all of this cannot be meaningfully reduced to probability most of the time, as cannot rain. So nowadays, the smartphone, of course, gives some probabilities of rain. Those keep changing. Many times they're totally wrong. Everybody can see that. And what's even worse, people don't understand what that could possibly mean. So we ran a study 15 years ago trying to test the public's understanding of probability of rain. This was a time that we were starting to use that in the news. There were no smartphones then that had this capability. And people were all over the place. What the meteorologists mean, which seems to be, there's a reference class of meteorological conditions and days that are similar according to those, and for those dates, for those conditions, if you could run the world many times, the probability eventually will be 30% or 80%. Very few people knew that. They started making up things that had to do with the amount of rain, with where it would rain, with whether meteorologists agree. So it is a mess. So not only it's hard to do it normatively, and if eventually you could reduce uncertainty to probability, it will be constantly changing. It will be hard to model even how this stochastic process would look, but also it's clear people don't understand it. So perhaps we need to back up and try to build models that help people make decisions or describe how people make decisions that are simpler. This is one of our motivations. And again, group is not approaching decision-making and uncertainty from your systemic perspective. I appreciate that. We're approaching it from other disciplines, such as cognitive psychology, operational research, or machine learning, which mostly look at individual or small group decision-making. And what we have to offer here is to offer faster models, very simple models. Because they're simple, they're also transparent. Non-specialists can understand them. And we claim that you can have speed and transparency together with accuracy. So here in italics, let's say the main thesis of the book. Usually there's this idea about effort performance trade-off. It still dominates pretty much everything in the behavioral sciences and in the management sciences. If you want to be more transparent, you're going to be less accurate. So, we wanted to formulate that and we wanted to test it rather than believing. So in the remaining of my talk, I will present a few empirical cases and just outline a theory. Again, we only have 12 minutes. So this is the previous election. It's more interesting because it was a surprise, at least from the perspective of big data analytics. Nate Silver's 538 said it's going to be Hillary. But it was Trump, as we all know. So Nate's model is completely transparent unless you're a statistician yourself. So how can it serve as a platform for policymakers and other stakeholders? On the other hand, if you don't look only at data patterns like statistics does, but you have a theory with content, you get ideas from the domain, such as, for example, history, as Alan Lichtman did, you can also produce predictions. So Alan Lichtman is a professor of history. He studied the history of all elections until 1980. Then he fixed these 13 keys, which is another word for attribute or feature. He doesn't change them anymore. Every time before the election comes, he assesses the keys and he applies his simple tallying rule, which says if 6 or more of these keys are false, the challenger will win. So most of the keys actually are framed in terms of the incumbent. And the intuition behind his theory is that it mostly matters what the incumbent does. So incumbents lose rather than challengers winning. So what he did back in 2016, a couple of months before, he fixed the keys, and he assessed that 6 were in favor of Trump. So he said Trump will win, and he was right. By the way, he continues his series of correct predictions, because this time he predicted that Joe Biden will win. The main point, though, is the contrast, right? You here have something very transparent. Everybody can debate. I mean, it could be a very incomplete theory, obviously, but we can all understand it and have discussions. And in this case, he was accurate. Of course, this is just one case. Another case in which we don't exactly have controlled data for accuracy is when we try to manage a multi-accident site. So this is something that exists in the 80s in the medical domain, in the emergency medicine domain. I'm not going to really read the whole thing through it, but you maybe get the point. It's a simple decision tree where the categories are somebody could be dying, so there's unfortunately not much you can do about them. Somebody could have minor injuries, so you can just let them be, and you should prioritize those who need immediate help or delayed help further down. This is a standard decision tree, except that it isn't. It's what we call a fast and frugal decision tree, because every time you ask a question, you can immediately make a decision. So that makes it fast, and it makes it passable, more passable than the usual decision trees, to keep in mind that, in fact, the practitioners who have been using that for about 40 years, including Lewis Cook, who wrote a piece on it in the early 2000s about how he used that to handle the disaster in the Twin Towers, they found it useful. We don't, of course, exactly know how well it works, but we know that they keep using it. So that must mean something, given all the self-correcting processes in the field. So this is another world. Before, we had attributes and they could all compensate for each other. They were fully compensatory. Here it's completely non-compensatory, because if the person is walking, minor category, you don't even need to look at all the rest. My third example has to do with the Google flu trends. Remember those? They don't exist anymore. For those of you who are younger, maybe you never knew. The others must remember. This is a case where the two words of completely non-compensatory and completely compensatory decision-making come together, because you have only one Q. So the Google flu trends use massive amount of data, big data, in order to predict the incidence of flu in the United States, in this case. It's completely transparent. We don't know what the variables are. You see here in the two panels have the same information, actually. They have the Google flu trends. This is the red thing, the red line. And across, on the x-axis is time, and on the y-axis is what we're trying to predict. The observed is the black line. And the recency heuristic, which I still haven't told you what it is the blue line. As you can see, despite the updates to Google flu trends, which were all after the fact, still the recency heuristic manages overall to outperform it. And you can see that a little more clearly maybe in the lower panel, where we have absorbed the observed into just an error for the two things. The blue line is closer to the zero error than the red line in general, and much less volatile. So can anyone guess what that recency heuristic would be? I already gave you a Q. It uses only one Q, only one feature. It's really the stupidest thing you could think about, and still it manages to beat all the effort that Google flu put in for years and years and years. It just uses the most recent observation that's available from the CDC. Of course, that's with a lag of a week or something. But if today I just go to the website and figure out and look what was the CDC report for last week, I'm going to predict better this week's influenza incidence in the US than if I did the Google flu trend. So I think that's a stunning lesson in how we don't know yet so well how to build complex models to understand, predict complexity in some cases, in this case. So we may just go simple and keep transparency as well. Of course, we didn't just cherry pick, but we did it the right way. We didn't only ask for practitioners what to do, but we also induced various models like Talling and fast and frugal decision tree statistically. We did out of sample cross validation and compared those with machine learning algorithms. Here you have CART. We did it also for support vector machines, which are arguably more accurate. If you can quickly read these scatter plots, you'll see that across these 64 data sets, there's a small difference only in the third decimal point in terms of how much more accurate classification regression trees are Leo-Breiman's trees compared to the fast and frugal trees or just Talling. And of course, we have measures of transparency as well, which I'm not showing you here, backup slides if someone wants. And there, of course, the heuristics do better. I think I'm gonna skip the theory because I think I got a cue that my time is up. The theory quickly is the bias variance dilemma. We have developed it to some extent. We also have conditions under which we can get, it's known that often simpler models have lower variance, but we're able to show that sometimes our models in the tasks we're looking at, which I'm conscious they're different from the huge system decisions you're looking at to have competitive bias. The question is, how does it scale up for your purposes? So if you want to read more about it, this is what we've done. We collected a lot of these things and decades work, and the last 3 years we've been writing this. Thank you very much.
Thank you very much, Konstantinos. Now we turn it to Rob Axtell. Rob Axtell works at the intersection of economics, behavioral game. He's a professor at George Mason University in Santa Fe, has published on several top journals during his career. The floor is yours now, Rob.
Okay, thank you very much for having me. Appreciate it. Glad to be here. I've not been to the DMDU meeting before, so it's looks like lots of good stuff going on here. I'm going to talk today about using new tools for understanding fisheries, and then not just fisheries overall, but in particular the behavior of fishermen, fisherwomen in the fishery. So maybe on the behavioral side, not unlike the previous talk a little bit. Okay, so quick background for those of you who don't know a lot about fisheries. The basic story is that you know, as a very practical matter in the world, I mean, fish are an important source of protein for humans. And of course, we have to harvest the fish from the ocean. So it's a coupled social natural system, as the little image shows here. The trouble is that many of these, many fisheries are in essence open access. Anybody can go and fish there. So in fact, these are hard to govern, hard to manage, and they end up being overfished. Okay, so this is the predicament that we find, you know, now 100 years into the kind of commercialization of fisheries, we find that many fisheries are basically in decline around the world. And then the mental model for the future is that climate change is going to exacerbate these management problems, and if it leads to some kind of you know, perturbation in the fish that are available to us, then it's, you know, has potentially, you know, a large impact going all the way back now to the, you know, the protein, this important protein source for humans. Climate can modify both where the fish live, but it's going to then you know, feed back into modifying how the fishermen, fisherwomen behave. And so I'm going to talk about basically how to model this this changing dynamic here. Okay, specifically, I'm going to talk about what's called the Poseidon Project. Now, this is a very large scale. I'm going to basically summarize. I apologize, you know, in the 12 minutes I have here, I'm going to summarize in, you know, 10 or 12 slides a 5-year effort between George Mason, UC Santa Barbara, Oxford, a couple other universities playing lesser roles, Arizona State, Hawaii, and then the Ocean Conservancy, which is a big NGO here in Washington. And this project has been supported over many years by some of the big American foundations, you know, Packard, Walton Family, Gordon and Betty Moore Foundation. Okay, so the goal has been to create better tools for managing fisheries through a complexity approach. So that's you know, how I fit into the session here. In particular, we want to move beyond what are really kind of a whole series of very unrealistic assumptions that are used at present for the actual management of these kinds of resources. So I'm going to be talking about fisheries. Most of the pathologies I'm going to mention here also apply to things like managing forests and managing groundwater. All kinds of renewable resources are typically modeled in very unrealistic ways. They involve things like, you know, assuming that the distribution of resources, like, you know, in this case, fish, are homogeneous. But for example, think about, you know, tuna in the Pacific. They're going to be very inhomogeneously distributed. we typically model the people who are doing the exploiting, the fishermen or the foresters or whoever, as being rational, when that may be far from the case. We typically can't deal mathematically with more than one or two of these exploiters, so we'd look at a representative exploiter, representative fisherman, for example, and then in constructing policies, have perfect knowledge of what's going on in the domain, which we can well imagine is going to be far from the case. So just to kind of put up, more detail on this and say that, what's been the state of the art in, for example, in mathematical bioeconomics. I mean, you basically use optimal control models on representative fishers who are rational and how they extract this homogeneously distributed fish. I mean, this sounds very archaic, but just going back one generation when I was in graduate school, this was the way that everything was taught and how we learned how these systems worked. But in reality, we know there are large numbers of heterogeneous people with different behavioral rules, different decision rules, and of course the thing that they're harvesting is very inhomogeneous in the environment. And then when it comes to policymakers, I mean, the old-fashioned approach was that policymakers could control this representative agent exactly, and then just figure out what the right policies would be to incentivize the fishers to kind of do the right thing at the sustainable level. So there is something called the maximum sustainable yield that is a formalizable concept within this domain in Colin Clark's book, and it is the kind of the main go-to idea when it comes to policy. But it's very hard to implement in practice because we have deep uncertainty about what are the fish stocks, what are the effects of policies on fishermen who are not fully rational, et cetera. And so we need to have new approaches to this, and I've written here adaptive policies. And then, so maybe the further background, for those of you who are not social scientists per se, let me just mention, the good news is that methodology is changing in the social sciences. So we have this, we're experiencing at the present time this transition from having aggregate data, at very rare intervals, quarterly, monthly, something, and that's basically produced by government, to having micro data that's potentially available in near real time. At the same time, we're seeing this transition from kind of low dimensional, simple analytical models, econometrically estimated, to very high dimensional representations in software that can eat all the microdata, right? So we have a variety of computational approaches, network analysis, agent-based models to do this. And so from a policy point of view, we say we're hopefully can see a transition from this kind of more top-down deterministic approach to modeling bioresources to something that's more kind of bottom-up and customized and adaptive, being very much aware of the fact that the world has deep uncertainty within it. So in fisheries, the way this manifests itself is as follows. In the US, at least, for many high-value fisheries, today we really have vessel-level microdata, including where has that vessel been, either from onboard GPS or from remote sensing devices. We have logs that are daily, written at the daily level. Every fish that gets caught basically are available in some of these logs. And in particular, when the fish are very high value, you even have onboard observers. And some of you will know a recent controversy associated with observers seeing things that they probably shouldn't be seeing, et cetera. I can come back to that at the end if there are questions about that. Main thing to say is that we can bring all these data together in models of individual vessels. We're going to model every single fisher in the system, in the fishery, model the behavior of individual captains, and we can meld all this and start to explore policies. Okay, so what is the Poseidon model? And this is, I say, this 5-year project we've been working on. We initially focused on West Coast groundfish. These are these big, kind of bottom dwellers in the Pacific, off on the continental shelf. So they're on the bottom, so they have to be caught with big trawlers. So the trawlers basically, as they engage in this behavior of dragging on the ocean floor. It turns out that about 100, a little bit less than 100 trawlers are in fact the entire West Coast groundfish fishery operation. So it turns out for several years now, there have been data on every single one of these trawlers. Okay, now these data are closely held, but they're, for example, Santa Barbara has them. And so we know actually where every vessel went every day and how much fish it caught. So it's also the case that against this background of these individual daily log data, there are also a whole variety of different policies that have been tried. And I'll show you some of them in a minute. And so we have this kind of natural experiment going on where in fact, policies have been executed. We see how the vessel commanders respond to that. And so we can create basically at full scale, since there's only 100 trawlers involved, at full scale, every boat, every vessel. And we basically try to represent every single fish that's caught. And then it turns out for different kinds of policies, the fishermen can actually trade some of the catch around. I'll get to that at the end. But we can even represent how the fishermen are trading their catches around. And then we can use this to design better policy. So this is kind of the big picture, the kind of the 30,000-foot view of it. And I'll get into a few details here without going into all the details. Basically, from the kind of data we have about what fishermen do, and from interviews with the fishermen, we can construct a kind of behavioral model, which, although I have not written it here, is kind of fast and frugal. It has many of the same properties of being kind of fast and frugal. What this is not a utility maximization calculation or kind of a profit maximization calculation for the individual captains. This is much more like, how can I get good information about where the fish are? How do I go there? What gear do I use, et cetera? It's very much kind of an adaptive approach, which is going to change on a daily basis. Okay, so they're going to update this every single day. The vessels go out daily, they come back daily, and they're going to update this based on what the conditions are. So we have this very general model here. Now, the point of me showing this is that it turns out we can actually, many of these different decision points here involve parameters. We can parameterize this model to represent basically the data we have on all 100 vessels. So this model is general enough to be parameterizable vis-a-vis the data, not so general that it's just that it's a model of everything. It's a model of fishers and the American West Coast groundfish. And then once we have that in place, we can now hook this up to what we're calling this kind of policy engine, where we say, well, what is the policy? Let's be sure the fishermen can make some profit, but let's not overexploit the fishery. And we can put this through this kind of this series of computational engines where we can progressively better model everything, and we can spit out better policies at the end. So as an example of that, just going to show you something here, which is from one of the papers that I'll mention at the end. And it's a very simple model where TACs here stands for total average catch, where basically the fishermen are given quotas that they can't take out more fish than what their TAC is, versus ITQ, which is individual tradable quotas, which is the policy where some fishermen can catch more than other ones if they're willing to trade it or trade it among themselves. And then what the top and bottom show in distinction here is simply when you model the fish as being homogeneous versus inhomogeneous, you get different results. And so what the colors refer to here, the dark colors are no good parts of the policy space. The lighter colors are good parts. And what you basically see is that we can reproduce kind of what's been intuitively learned over the last couple of decades, that these individual transferable quotas, when you in the context of having fugitive fish that can move around but that are inhomogeneously distributed, this down to the lower right hand corner, we can reach high levels of welfare here, 1.3 levels of this policy score. Anyways, the main thing to say is that the model each dot here represents kind of a separate run of the model in different policy space, and we can track different performance of the model. Another way to say that is we can also create then now, where in the previous plot I'm just showing TAC versus ITQ, but we can actually also look at hybrid policies, things like what if we make certain marine protected areas, MPAs, where people can't fish, but we also can modify the season length. Well, we can look at these things computationally through the ABM, and we can say, holy cow, we can have a situation where we have a large marine protected area, like what it shows for the plot B there, or we can have kind of smaller ones, but we can then modify the season, and we get this kind of, in essence, this trade-off surface, right? We get this trade-off surface where we can say we can have a lot of catch or lesser catch. We can even decide which we can control kind of which boats are getting the catch. So the main thing is we can kind of illuminate the trade-offs that it really happens. So instead of the policy authority merely saying we're going to be in this part of the policy space, we actually can paint these pictures of the policy trade-offs and then let decision makers decide where they want to operate. So I don't have a lot of time here, but just maybe to get into the kind of where this thing has gone from this base case ostensible success. And by the way, I didn't go through it, but on the previous model, we interacted with the NOAA policymakers and have had a constructive relationship with them and how they set policy for those groundfish. But of course, many fisheries around the world don't have good data, don't have good monitoring. For example, in Indonesia, where fishing is done by small vessels, typically we don't have good data. But we tried to deploy the model to that environment as well. In the case of having, the California groundfish, although they're highly localized, they typically are going to always be there. It's in the case of Pacific tuna, the fish are going around in schools, and so they're much more irregularly distributed. So can we apply this modeling approach to this too, and with say much bigger fishing vessels, et cetera? And so there's a project underway that does that. And then of course both of those fisheries, because the tuna are not under one jurisdiction, and because Indonesia is loosely governed, in essence these are unregulated fisheries. So how to apply this? It's easy to apply it when we have NOAA governing the West Coast groundfish. Hard to apply in unregulated fisheries. And the final thing to say here is that can we, when it comes to climate change, we have shifting habitat, et cetera, new gear can be used, et cetera. Can we use this model in the context of climate change? I'm not going to get into the details, except to say that this is in fact an important focus of our current work with Poseidon. So the first 5 years of Poseidon, building the first groundfish model, then doing the first 3 bullets of extensions, and now we're trying to extend it into climate change issues. So the summary of all this is that fisheries are an example of where we need new perspectives to deal with them, and the complexity perspective is a useful one here, in the context of ABMs. So we're transitioning from microdata to richer models. The Poseidon model, which is a public domain piece of software available to anyone who wants it as a new tool for doing these kinds of policy syntheses, used in the West Coast groundfish, being applied to other regions and problems, and not newly being used to model climate change things. And our sense is that it's exactly this kinds of complexity approach that's going to be needed if we're going to successfully manage the various effects of climate change. Now, this is a big team that's been involved with this. I put a bunch of names here. These are UCSB people, Oxford people, et cetera, Ocean Conservancy, and the 2 principal publications that have come out. One in sustainability science, one in fish and fisheries. And if anybody wants to learn more, feel free to contact me offline. Thank you.
Thank you very much, Rob. Wonderful presentation. Let's open up for questions. I have one from Patrick Rick to you, actually, Rob. What are your thoughts on the common divide in fisheries representation in economics as a stock and flow system versus predator-prey theory in the trophic ecology field? For example, the Lockyer-Volterra equations.
Yeah, right. So it's very important. What we've learned is that a very important aspect of these kinds of models is how do you properly represent where the fish are, and that's the blue box here, the ocean ecology model, and there are various ways to do that. Of course, the economic models typically do it very simplistically, and there are much more complicated ways to do it. It seems like depending on how much resolution you need on the policy side, you may not need to have super detailed ecology, but in some models, of course, where the fish have complex age structure, et cetera, you need to have some more of that. Let me just mention that we've used ABM here to model the fishing fleet, the fishing vessels, right? But there are some people who have talked about using ABMs to model all the fish, right? To have every individual fish be an agent as well. That's kind of the research frontier. That work has kind of just started up, and some of you may have seen a little bit of it. There's some very beautiful animations associated with having GPUs, using GPUs to represent millions and millions of fish, and so that's the state of the art. And I think that how that unfolds is a research question at this point.
Thank you very much, Rob. I see a lot of questions have already been addressed by presenters through the chat. I don't know if anyone else wants to ask another question. Maybe you can unmute yourself, and maybe we have time for one more question.
Well, I'll throw in a question. Just great presentations all. Rob, how do you treat uncertainty in the model? I mean, is it all in the adaptivity, or what? And are there any formal representations?
Yeah, so I kind of skipped over all those details, Rob. But basically, overall, we when there's kind of parametric basis for the uncertainty, for example, like when the policymakers go out, and it's the policymakers' job to do what's called stock assessment. How many fish are actually in the ocean, right? And so they can get kind of parametric bounds for uncertainty there. One thing we get from looking at these logbooks is we can try to build up, how much uncertainty is there in the various parameters for what the fishermen are actually going to do. So now those, of course, 2 different kinds of uncertainty interact, and all I can really say about it is that it's really through the model that kind of those uncertainties get propagated. So what we don't have in this model is typically some kind of there's some Weibull distribution of something or other, and that gets propagated through. No, we don't do anything like that. We just basically use the kind of it's the way the way the behavioral rules interact with the natural uncertainty that plays out. Now it's all constrained, as I mentioned a second ago. It's all constrained by, in essence, the ocean ecology model. And so my sense is that if I had to summarize, looking at this picture right here, my sense is that much of the real uncertainty is actually in that ocean ecology box. That is, how the world really unfolds underwater is something which we don't know a lot about, and so very deep uncertainty on that at present.
Perfect. Thank you very much, Rob. Well, with that, we conclude this session. We thank you, Rob, Konstantinos, Tim, Rob Lampert for participating in the session. It was a pleasure. I'm gonna leave the chat open just for those who want to maybe interact a little bit more in the chat. Thank you very much for making time today.